This is the Truss Analysis Coding Project prepared by Sim, Stefan, and Collin. It's a quick intro. Truss systems have many different applications and diverse structures. As seen on the top right, that is a brace-ribbed arch, which in this specific application is used as a bridge. In order to solve a truss system, they usually follow the same pattern, that being identifying the components, numbering the members, numbering the nodes. This gives a general understanding of what goes where and how to set up an equation to solve for those unknowns. So then the next step would be generating a system of equations, which includes all of the members and all of the nodes. And then finally you solve for the unknowns, which is typically the member forces. So applications, as mentioned in the brace-ribbed arch, is like bridges. Trusses are also found in building structures. And in the bottom right, you can note that that truss was used in a fire safety study. And what this group did was they followed simple procedure, kind of like we do in this project, and they changed things like the Young's modulus, cross-sectional area, the weight of the truss, the material used, and they saw if the truss met the fire safety regulations. Moving on, for this project, we had many different problems we had to solve. Each problem built off the prior one. So for example, what we did in part A would then be used in part B, and then what we found in part B would then be used for part C, etc. What we had to do is we were given a pseudocode, and we had to take that code and alter a text file, and we had to solve the system in terms of member forces. And from there, in part B, we had to solve the same system, but using different increments of theta, starting at 20 degrees and moving up to 80 degrees using increments of 5 degrees. And then part C, we had to follow the same procedure that we did in part B, but we had to use smaller increments. This allowed us to optimize the truss and find at what theta the truss system would then be optimized. Part D, we had to return a table using the theta value that we found in part C, and it gave us desired outputs. This includes the node numbers along with each member, the member number itself, the force in the member, the stress in the member, and the length change of each member. For part E, we had to move on to a statistically indeterminate system. Here we are given a separate pseudocode, and we had to continue the steps that we previously did, but then move on and generate a global matrix, which we would then be able to plot the undeformed and deformed truss as a comparative measure. Part F was the same thing as part E, except we had a different truss design. We followed the truss in the top right, and we had 3 different load conditions.
Here's our approach for solving truss systems using Matlab code. We first want to label our nodes and elements. On the right-hand side, you can see that we have our nodes labeled with letters and elements labeled with circled numbers. After labeling nodes and elements, we want to determine the connections between nodes, which will be our node from and node to values. For example, element 1 is from node A to node B. Then we want to determine the magnitude, direction, and location of external forces. You can see that we have 3 external forces, all of which are 10 kilopounds in magnitude. One at node C, one at node E, and another one at node G. They all point in the negative y direction. Then we want to determine the reaction nodes and directions and which nodes depend on theta. Then we want to create separate input files for each part of the project. All these input files will need their own function files because they have different data in them. Therefore, one single function can't read all input files correctly. These functions will also compute and output different values. Moving on to the implementation of code, we have our script file on the right, which implements all our functions using their corresponding input text files. For part A, we needed to solve the truss shown here. You can see the function used to solve the system on the right and its input file. In the input file, you can see the data needed to solve the truss system on the left and their explanation on the right. For example, this 4 at the top is the number of nodes in the truss. Then for part B, we use the function solve truss B and take truss B as the input text file. Solve truss B is just the part A code modified to increment theta by 5 degrees and compute the cross-sectional areas and weight. Part C uses the same function as part B, but the input file for part C is truss C, which increments theta by 1 degree as opposed to 5 degrees. Continuing with the implementation of code, we have part D here, which uses the function solve_truss_d and takes truss_d as an input file and outputs the cross-sectional areas, stresses, and the change of length in each element. Part E uses solve_truss_e, which is a function modified to solve statically indeterminate truss systems. This function takes truss_e as its input file and outputs the displacements and stresses. Part F uses the function solve_truss_f. There's 3 loading cases we look at in part F, which are shown on the right side. For each loading condition, we use code to plot the deformed and undeformed truss and output the displacements and stresses.
Alright, so for the results, we will show our outputs by running the code that solves problems A, B, C, D, E, and F using the trusses below. Alright, so we're in Matlab. So for part A, the function was given, so I will run it. This is the output. For part B, I had edited the code from part A so that I could solve for the area and the total weight using 5-degree increments. And this is our output. For part C, it uses the same function as part B. It just increments by 1 degree instead of 5 degrees for theta. And then part D, it outputs into a table output text file all of the forces, stresses, displacement, weight, and area, as you can see. And then parts E, F, for all loading cases, they plot the trusses with different loading conditions. And the undisplaced truss is in blue, and the displaced truss is in red. And so these are all. Let's head to the PowerPoint. On the right for part A, these are the output forces in each element and at each reaction for the truss. For part B, on the right, we have the solved weights of the truss and the cross-sectional areas as theta increments by 5 degrees. For part C, you can see on the right that the cross-sectional areas are solved again, being 1 degree increments of theta as well. And the optimal angle that we found using part C is 57 degrees. For part D, on the right, that's the table generated from the code. It shows the connectivity, cross-sectional areas, force, stress, and length change in each element. For part E, the figure on the right shows the generated plot of the deformed, which is in blue, and the undeformed truss, which is in red. And on the right of that is the displacement values of each node. For part F, there is various loading conditions, and the forces applied are on the right, shown below. For loading case B, the forces on the right are all pointing upwards, and that's the plot generated. And for loading case C, the forces are in differing directions, and that's the plot for load case C. In conclusion, analyzing truss systems has many applications. By generating a system of equations and solving for the forces in each member, we can derive different outputs, like the cross-sectional area, the stress, and the displacement of each member. Normally, if you were to compute this by hand, it would take a very long time. But using Matlab, we're able to compute it in a more efficient way. And also, Matlab isn't just good for truss systems, it's good for any other systems, like in physics. So I want to leave you with a question. What other system can you model with Matlab? Thanks for watching.